Welcome back to the deep dive. If you're building any modern application today, chances are the most difficult engineering challenges you face aren't about raw CPU speed, they're about data. We are living in an era of, well, data-intensive applications.
Exactly. And when you dive into the technology stacks, the NoSQL databases, the distributed queues, the complex caching layers, you are immediately just bombarded with buzzwords.
Oh, yeah.
Big data, sharding, eventual consistency. It can feel like standing in front of like 1,000 puzzle pieces and being told, build the next Facebook.
Right. It's a lot.
Okay.
So our mission today is to cut through that noise. We're taking what we hope is the ultimate shortcut, diving deep into the foundational principles, the things that underpin every successful data system, whether it's, a simple PostgreSQL instance or some globally distributed cluster handling petabytes. We're not just looking at how specific databases work, we're trying to figure out the why.
Yes, the why. Exploring the engineering trade-offs that really dictate modern architecture. And that why always comes down to three cornerstones. These are the attributes that must be thoughtfully, deliberately engineered into the system, right from day one.
The big three.
We call them the three pillars: reliability, scalability, and maintainability. If a system fails on any one of these, its success is limited, regardless of how fast or novel its technology might seem.
So we're framing this discussion not as abstract goals, not just wishful thinking, but as concrete attributes, things that determine whether your product survives its first big profit spike or, its first major code base overhaul.
Absolutely.
Let's start with the most critical commitment, the promise to just keep working, reliability. Hashtag one. The three pillars of data systems: reliability, scalability, maintainability.
Reliability is, well, it's simple in definition. The system continues to work correctly, performing its required function, even when faced with adversity.
Right.
It must tolerate faults and maintain acceptable performance. But the first thing we absolutely must clarify is the difference between a fault and a failure. They're not the same thing.
Okay, that distinction feels crucial. When I hear fault, I usually think breakage. Something's broken. But in system design, a fault isn't necessarily a service interruption, is it?
No, not at all. A fault is merely a component deviating from its specification. Think of a hard drive throwing a bad sector, or maybe a network cable momentarily glitching. That's a fault.
Okay.
A failure, on the other hand, is the system as a whole stopping service to the user. The entire goal of fault-tolerant engineering is to build systems where faults do not escalate into failures. We are actively building reliable systems out of components we know are inherently unreliable.
Building reliability from unreliable parts. Okay, so let's break down where these faults actually come from. Our sources categorize them into three major areas, starting with the classic hardware faults.
Right. Hardware faults are often the easiest to anticipate and mitigate because they tend to be random events, disk crashes, permanent RAM failure, network card issues, maybe a power loss.
Usual suspects.
Yeah. These faults are generally rare, statistically speaking, but they happen. It's inevitable. So the standard engineering response here is robust redundancy.
And when we talk about redundancy, what are the common approaches? We hear about things like RAID or just using multiple machines, right?
Exactly. Take RAID. The redundant array of independent disks is a simple example. It ensures that if one drive fails, the data can be reconstructed from, say, a parity drive or a mirror drive.
So the fault doesn't cause a failure.
Precisely. The fault, the dead drive, doesn't cause a failure, data loss, or system shutdown. In modern distributed systems, this just scales up. If one server in a cluster dies, the workload instantly shifts to another replica. The cost of downtime is almost always higher than the cost of that redundant hardware.
Makes sense. But the next category, software errors, feels far more complex because they aren't random. They are systematic faults. They're kind of baked into the design.
That's what makes them so insidious, so tricky. These are the bugs. Maybe a memory leak that only appears after 48 hours of heavy use, or a faulty assumption about a maximum integer size, or maybe a dependency that misbehaves only when network latency spikes. They often lie dormant until a specific, unusual set of circumstances triggers them. And the worst kind is the cascading failure.
Oh boy.
Yeah, where a small, systematic fault causes one component to overload, which then overloads its neighbor, leading to this chain reaction that can bring the whole house down.
It's the Achilles heel of complex microservice architectures, isn't it? You think you've isolated things, but then one unexpected error in a seemingly minor service becomes a dependency nightmare.
Absolutely.
So if there's no single silver bullet, How do engineers even begin to tackle these systematic faults?
It requires meticulous defensive programming and system design. I mean, rigorous testing is mandatory, obviously. But beyond that, you need things like process isolation, making sure that a crashing component can't immediately corrupt the memory or state of its neighbors. Our sources also highlight the importance of constant self-checking. For example, if your system involves message queues, you should constantly verify that the number of messages consumed actually matches the number produced.
Like an internal audit.
Sort of, yeah. Raising an alarm if there's any discrepancy, even if the system appears to be running fine. This helps detect those hidden faults before they become user-facing failures.
And finally, we have the most pervasive and arguably the most difficult fault to predict or eliminate: human errors.
Yeah, because humans design, code, configure, and operate these massive systems. So the design itself must be centered on minimizing opportunities for human error.
Right.
A famous example is, an engineer forgetting a decimal point in a critical firewall configuration rule, leading to a major outage. These aren't malicious acts. They're just mistakes made under pressure, or maybe because of complex interfaces.
Which speaks directly to that third pillar we mentioned, maintainability, doesn't it? If the system is too complex to operate safely, it's inherently not reliable.
Precisely. To mitigate human faults, the system needs excellent operability. This means providing good abstractions and really well-defined tools so that routine tasks like deploying an update or modifying a configuration parameter don't require deep esoteric knowledge of the system's internals.
Make it easy to do the right thing.
Exactly. We also need robust, automated deployment systems that facilitate quick, low-stress rollbacks if an error does occur. The goal isn't to blame the operator, it's to engineer the system so that human error is caught and contained immediately, or ideally, prevented.
And we keep circling back to why this matters commercially. Why should, say, a C-suite executive or a product manager really care about whether we use RAID or implement self-checking message counts?
Because reliability is the absolute foundation of trust. And trust gets formalized in things like service-level objectives, SLOs, and service-level agreements,
That's contract.
Right. These are contractual guarantees to customers about the uptime and performance of the service. If you guarantee 4 nines of uptime, that's 99.99%, you're promising less than an hour of downtime per year. If you fail, you often pay the price through financial penalties or refund clauses. Those contractual promises are a direct translation of the engineering work done to manage faults.
Okay, that sets us up perfectly for our second pillar, scalability. This is all about how a system handles increased load. But before we even discuss scaling solutions, we have to define what load actually means in context.
You really must define your load parameters quantitatively. Load parameters are the specific metrics that characterize the load on your system. For a database, it might be reads per second, or the cache hit rate, maybe the right transaction rate.
Okay.
For a chat system, it might be the number of active users simultaneously sending messages. You cannot select the right architecture or even know if you need to scale until you have clearly quantified these parameters for your specific case.
So we know the load. Now we need to define the expected performance under that load. There's the well-known concept of latency versus response time. Can you quickly clarify that for us?
Sure. Latency is the time a request spends waiting or undergoing internal processing within the system itself, just the waiting part.
Got it.
Response time is the total duration the client experiences, starting from when they send the request until they receive the full response back.
So it includes network travel time and everything?
Exactly. Response time is the true measure of user experience because it includes network delays, any issuing delays, and the system's internal latency.
Now, when people report performance, they often look at the average, or maybe the median, the 50th percentile. That sounds intuitive, right? If the average response time is 100 meters, that sounds pretty fast. But our sources warn that relying solely on the median is dangerously misleading. Why is that? Why is the median insufficient for a reliable system?
Because the median tells you absolutely nothing about the experience of the users who are receiving the slowest requests. If your median is great, but your 99th percentile is terrible, you are actively frustrating, potentially, your most engaged or maybe even your most valuable customer.
The outliers matter.
They really do. These high percentiles, the 95th, the 99th, sometimes even the 99.9th, are what really capture the worst-case user experience.
I remember reading the famous Amazon anecdote about this. They found a direct correlation between slow response times at those high percentiles and actual revenue loss.
Absolutely. The difference between the 95th and 99th percentile response time is often massive. And it's these extreme requests that are most often affected by things like queuing, random network jitter, or maybe garbage collection pauses in the runtime. Yeah. Amazon, for example, famously prioritized optimizing the 99th percentile performance. However, they also realized that optimizing the 99.9th percentile, so the slowest 1 in 1,000 requests, often involved throwing enormous amounts of engineering time and hardware at really transient network events or hardware anomalies. It yielded diminishing returns compared to the cost.
So setting the service level objective, the SLO, at, say, the 99th percentile becomes a pragmatic engineering trade-off. You ensure a great experience for almost everyone without bankrupting the company trying to eliminate the absolute rarest, most chaotic performance spikes.
It's finding that sweet spot between user happiness and engineering feasibility. So once we had defined our targets based on these percentiles, then we can look at approaches to actually manage load growth, the classic scaling up versus scaling out.
Scaling up, or vertical scaling, means bigger, more powerful machines. Scaling out, or horizontal scaling, means distributing the load across many smaller commodity machines, the classic shared nothing architecture. Scaling out is the modern buzzword, right? It's the core promise of distributed systems. But is it always the right answer?
Not at all. It's where the trade-off gets really complex. Distributing load across many machines scaling out is absolutely necessary for truly massive scale, but it introduces incredible operational and coordination complexity.
Yeah.
For many organizations, honestly, using a few highly powerful machines scaling up is simpler, cheaper, and often more reliable, especially when you're dealing with stateful systems like traditional relational databases.
Okay, why does complexity explode when you try to scale out a stateful system like a database?
Because you suddenly have to deal with coordinating state across multiple machines. You have to manage replication lag, ensure consistency across potential network partitions, handle inter-process communication failures. It's a whole new world of problems.
Right.
If you have stateless services, like a web server tier, you can easily just throw a load balancer in front of 50 VMs. Simple enough. But if you have a single relational database containing all your critical transactional data, moving that to a distributed, scaled-out design, like sharding, fundamentally changes the way you write queries and the guarantees you can even make about the data.
It's a huge architectural shift.
It is. The sources confirm that a pragmatic mix is almost always best, often favoring reasonably powerful machines over just an ocean of tiny, impossible-to-manage nodes.
We also hear about elastic versus manual scaling, elasticity, automatically spinning up resources when load spikes unexpectedly. Sounds like the perfect solution for unpredictable traffic.
It does sound perfect, but unpredictable load is often a feature of stateless front ends, not necessarily stateful back ends. Automatic elastic scaling of a database is an incredibly complex engineering feat. Very few systems do it truly well. Manually scaled systems, where capacity is planned, monitored, and adjusted by human analysis, are often simpler, more cost-predictable, and frankly, have fewer operational surprises, particularly in critical back-end infrastructure. The decision really depends entirely on how predictable your load parameters actually are.
Okay, our final pillar is maintainability. This often gets overlooked, I think, in the excitement of shipping new features or chasing performance gains. But our sources stress that in the long run, maintainability dictates the system's success, maybe even more than the initial peak metrics.
Oh, absolutely. If the system is not maintainable, every new feature becomes exponentially more painful to implement. It introduces opportunities for those systematic faults we talked about, and it just slows the velocity of the development team to a crawl.
Technical debt catches up.
Exactly. Maintainability ensures that the life of the engineering and operations teams working on the system over time is productive. We break this down into three facets: operability, simplicity, and evolvability.
Operability sounds like making routine tasks easy for the operations team. What are the key tasks that need simplification here?
It's all about smooth production management. We need clear monitoring to quickly identify anomalies, robust logging to trace the causes of failure, and rapid processes for service restoration and debugging when things go wrong.
Right.
Crucially, it also involves excellent capacity planning and reliable security patching practices. If it takes like 3 days and 7 different configuration file edits just to roll out a critical security patch, your system has poor operability and thus poor maintainability. Good automation tools are really the hallmark of strong operability.
Next up, simplicity. That sounds obvious, but complexity is kind of inherent in large systems. How do we manage that complexity effectively?
Complexity is the enemy of safety and speed. It makes systems difficult to understand, especially for new team members joining the project, and it provides hiding places for those tricky systematic faults. The key to simplicity is robust abstraction.
Abstract.
Good abstractions hide immense complexity underneath a well-defined, easy-to-use interface. Engineers can then focus on the specific service they are building without having to worry constantly about, say, how the underlying network protocol or disk indexing actually works.
But bad abstractions.
Oh, poorly chosen or leaky abstractions, conversely, can expose complexity where it shouldn't exist, making things even harder. Good abstraction is an art.
And finally, evolvability or agility, which sounds like the natural consequence of having a system that's both simple and operable.
Exactly. Since requirements change constantly, new markets emerge, user behavior shift, new regulations come into play, the system must be easy to adapt and modify. If the system is simple, with good abstractions, engineers can change a small part of the system without causing cascading effects across the entire codebase.
Less fear of breaking things.
Right. This ease of change is directly tied to developer velocity. If you can't evolve your system effectively, you fall behind the competition, regardless of how reliable or scalable it was initially.
So reliability, scalability, and maintainability. Those are the high-level goals, the pillars. Now let's move up the stack a bit to the first critical design choice we make after defining those goals. The data model itself. #tag2. Data models and query languages deep dive.
Okay, the choice of data model. This dictates the relationship structure, the typical query patterns, and ultimately the complexity of the application code you end up writing. For decades, the relational model, established by Edgar Codd back in 1970, was absolutely king.
Yeah, for a long time.
Its dominance for over 30 years is truly remarkable in the history of computing. Tables, rows, foreign keys, strong guarantees. It's the standard.
But then the NoSQL movement arrived and threw a bit of a wrench into that dominance. It was driven by needs like massive horizontal scalability, more flexibility, and solving what developers often found most frustrating, the object relational mismatch.
Ah, yes, the impedance mismatch. It's that inherent friction developers face when trying to translate the data structures they use in their application code, which are often object hierarchies, nested maps, maybe tree-like structures, into the flat, rigid relational schema of tables and rows, and then translating it back again when reading the data out.
That process of splitting objects across multiple tables.
It's known as shredding the data.
Right. I can definitely relate to that frustration. If I have, say, a user profile with multiple addresses, education history, maybe job positions, in a relational model, I have to create separate tables for each of those one-to-many relationships and use foreign keys to stitch them all back together on every single read. It feels like writing a ton of boilerplate code just to deal with the database structure.
It's kind of the developer tax you pay for that relational rigidity and its guarantees. And this is exactly where document databases like MongoDB, for instance, really gain traction.
Because they match the application structure better.
Often, yes. If your data naturally lives in a document-like structure, where you typically load the entire user profile, including all its addresses and positions all at once, then storing it as a single JSON or XML-like object can simplify the application code dramatically. You avoid that whole shredding process entirely.
But as always in data systems, the simplicity must introduce a trade-off somewhere, particularly regarding relationships between different documents, right?
Exactly. Relational databases are optimized for joins, efficiently linking data across multiple tables using foreign keys. Document databases, on the other hand, often have weak or sometimes even non-existent join support built in. So if you need to link, say, a user document to their specific regional sales branch document or to their list of preferred vendors, which are separate, maybe frequently updated entities, you often have to manually resolve those references by making multiple queries from your application code. Fetch the user, then fetch the branch, then fetch the vendors.
That sounds like, well, a potentially dangerous form of simplicity. You're trading complexity inside the database engine for potentially more complex and maybe less performant application code outside the database.
That's the trade-off. Precisely. And interestingly, this isn't a new problem at all. This dilemma actually echoes historical database models from way back in the 1960s and 70s. Before SQL became dominant, we had the hierarchical model, like IBM's IMS, and the network model, like Codasol.
Tell us more about the historical parallel with codicil, because that's often cited as the kind of nightmare scenario that SQL saved us all from.
Yeah, codicil was a network model that stored relationships as explicit pointers between records, like memory addresses. To query the database, you didn't write a nice declarative statement like select the data. Instead, you wrote intricate imperative code that moved a conceptual cursor along specific predefined access paths. You were manually following the pointers and iterating over lists in your code.
Wow. So the developer wasn't saying what data they wanted, they were explicitly telling the database how to physically navigate its internal structure to find it.
Precisely. This made the query code incredibly complex and extremely fragile. If you decided to change the underlying physical data model, say, you wanted to index relationships differently for performance. Vast amounts of handwritten application code that relied on those specific imperative paths had to be completely rewritten.
Ouch.
SQL's declarative approach solved that rigidity by allowing the database optimizer to handle the how. Now, while modern document databases share some structural similarities with the hierarchical model, they thankfully avoid codicil's really painful imperative access paths. They usually use simple, unique identifiers for references, which is structurally quite similar to foreign keys in relational, just without the enforced integrity, maybe.
Okay, that brings us to schema enforcement itself, which is fundamentally different between the two models.
Right. The relational approach is generally schema on write. The data must conform to the predefined schema, the data types, the constraints, the table structure, before it can be successfully written to the database. This offers strong guarantees, kind of like static type checking in a programming language. If the data format is wrong, the database rejects it immediately.
The document model, conversely, is often described as schema on read. What does that mean?
It means the schema is implicit and much more flexible. Enforcement, if any, happens in the application code when the data is read back out. This is more like dynamic type checking in programming.
So changes are easier.
Yes. If you decide to change a field name from, say, full address to split it into street, address, and city, you could just start writing new documents in the new format immediately. The trade-off, though, is that your application code must be robust enough to handle reading older documents gracefully. It needs to check if the old field exists, maybe apply a fallback rule.
So it pushes the responsibility.
It pushes the responsibility of maintaining data integrity and handling format changes from the database layer up into the application layer. This flexibility is a huge advantage for rapid schema evolution, especially early in a project. But it requires more discipline in the application code.
We mentioned SQL's declarative power earlier, and it feels worth dwelling on why that level of abstraction is so fundamental to building high-performance, maintainable data systems.
The beauty of a declarative language like SQL is its separation of concerns. You declare what data you want. Crucially, you don't tell the system how to execute the query. You don't specify which index to use, which join order is most efficient, or how to allocate memory for the operation.
And that's critical because it empowers the query optimizer.
Yes, exactly. The optimizer, based on its internal knowledge of the data distribution, the available indexes, the storage structures, and various statistics, can choose the most efficient execution path for your declared query. If you later improve the indexing structure, the same query just runs faster without the application code changing at all. If you had to use an imperative language like codicil, every performance tweak would potentially mean rewriting query logic scattered across the entire code base. It's a maintenance nightmare.
We even see this principle outside of databases, like in modern web development. CSS is declarative. You declare that all P elements inside an element with class article should be read. You don't write imperative JavaScript code saying, loop through all elements, check if there are paragraphs, check their parent's class, and then set the color property. It's much more abstract.
That abstraction is why declarative languages are so powerful and really necessary for complex data manipulation. Even non-relational systems often try to achieve some level of this abstraction, sometimes through frameworks like MapReduce.
MapReduce, how does that fit in?
Well, while MapReduce is often thought of for large-scale batch processing, it can also function as a highly constrained, read-only query mechanism, particularly in some NoSQL systems like older versions of MongoDB or CouchDB. It allows for bulk operations on documents in a somewhat declarative way, though it's still generally less flexible and powerful than a full SQL optimizer. Hashtag 2.3. Graph-like data models.
Okay, what if the relationships in your data are not just complex, but they are the most important part of the data itself? If you're building, say, a social network or a recommendation engine, or maybe a complex dependency tracker for software components, you're just drowning in many-to-many links. This sounds like the domain of graph data models.
Absolutely. Graphs become a much more natural and flexible fit when the connections between entities are paramount, and the structure of the data itself might be constantly evolving. Modeling data as a graph makes traversals and relationship analysis much more efficient than trying to do the same thing with, say, multiple deep joins in a traditional relational database. Those joins can get prohibitively slow, especially across several degrees of separation.
The leading structure used here seems to be the property graph. How is that actually structured?
It consists of three primary components: vertices, which are the nodes representing entities like people, products, or places. Then you have edges, which represent the relationships or connections between vertices like knows, purchased, or located in.
Okay.
And critically, you have properties that can be attached to both vertices and edges. The properties on the edges are particularly key. They allow relationships themselves to carry metadata. For instance, the date a friendship started, or the weight of a professional connection, or the cost of a flat path.
And the strength of this model is its flexibility and especially efficient traversal, right? Following those connections.
Absolutely. You can traverse the graph incredibly efficiently, going forward or backward along edges, filtering by different relationship labels. For instance, you could query all products influenced by a specific user's purchase history by traversing purchased edges that maybe belongs to category edges, and then influences edges, all potentially within a single fast graph operation. This flexibility is really critical for modeling complex real-world data scenarios, like regional hierarchies where the structure isn't uniform, or tracking intricate medical dependencies like allergies across ingredients and recipes, things that are awkward in tables.
So to query these property graphs, we need specialized declarative languages. Something like Cypher is often mentioned, which looks very different from SQL.
Yeah, Cypher is quite popular, especially with Neo4j. It allows you to express your query almost visually, defining the pattern you are looking for using ASCII art, like person.friends with other person. It specifies the node types, the edge type, the relationship label, and the direction of the relationship you're interested in. For these kinds of relationship-heavy queries, it's often far more intuitive than writing complex multi-table joins in SQL.
We also hear about triple stores. How do they differ?
Triple stores are another graph model, often associated with the semantic web. They store data literally as billions of subject-predicate-object triples, like Jim knows Jane. They are queried using a language called SEPI-RQL, which is also declarative, but designed specifically for triple patterns.
And underpinning many of these declarative graph query systems, you mentioned the logic programming language Datalog. That sounds pretty fundamental.
It is. Datalog serves as a kind of foundational framework for defining powerful logic-based rules and relationships within the data. It's older than SQL, actually.
Datalog introduces this concept of defining rules that allow the system to derive new facts or predicates from existing data. Can you give us a tangible example of how Datalog's rules enable something that SQL might struggle with?
Yeah, the key strength is handling recursion gracefully. Imagine defining a complex organizational hierarchy in a company. In SQL, finding every single employee who directly or indirectly reports up to the CEO often requires complex, sometimes slow, recursive common table expressions, CTEs.
Right, those can get tricky.
In Datalog, you can define it much more elegantly with two simple rules. First, a base rule that defines the immediate reporting relationship, like reports to employee manager. Second, a recursive rule that states if X reports to Y and Y reports to Z, then X transitively reports to Z. You define the logic of the relationship.
And the Datalog engine just keeps applying that recursive rule until no new reporting relationships can be derived.
Correct. It essentially performs a transitive closure over the specified relationship, very efficiently determining all the indirect connections, like finding all the cities contained geographically within North America, even if they're only immediately contained within a state, which is contained within a country, which is finally contained within the continent. It derives this knowledge based on the rules you provide, which is what makes graph structures and languages like Datalog so effective for complex analysis. #3 storage and retrieval deep dive.
Okay, moving down the stack even further, we arrive at the core mechanics of how the database actually stores and retrieves information on disk or in memory. It all really centers around the concept of the index.
The index is the vital signpost, right? It's a derived data structure that helps the system quickly locate the data associated with a particular key or maybe a range of keys. But we immediately revisit that constant trade-off we keep mentioning. Indexes speed up reads, significantly sometimes, but they introduce overhead and inherently slow down writes.
Right, because every time data is changed, inserted, updated, deleted, every associated index structure must also be consistently updated to reflect that change. We're paying a write penalty up front for faster read performance later, hashtag tag 3.1, data structures that power your database.
Okay, let's start with the simplest form of index, the hash index. This is the engine behind many basic key value stores you might encounter.
It's essentially just a large append-only file, like a log sitting on disk.
Pretty much, yeah. And alongside it, you keep an in-memory hash map. This map links the key, like a user ID, to the specific byte offset of its corresponding value within that big append-only log file on disk.
So writes are fast.
Writes are extremely fast because it's just sequential appending to the file and updating the in-memory map. And point lookups for a specific key are also fast. It's a simple hash map lookup followed by usually a single disk read at the known offset. But it has a critical feeling we need to understand. It does not support efficient range queries.
Oh.
You cannot efficiently ask, find all users whose ID falls between 1,000 and 2,000. You can only ask for ID 1,000 specifically, then 1,001, then 1,002, and so on individually. This completely defeats the purpose of using an index for range scans.
So to solve that range query problem while hopefully retaining some of that high sequential write throughput, engineers developed the SS table, or sorted string table, and this forms the basis of LSM trees.
Right, the key innovation here is sorting. If you keep segments of key value pairs sorted by key, these sorted segments are the S tables, you instantly gain the ability to perform efficient range scans. You just find the start key and scan forward. Furthermore, because the data within an SS table segment is sorted, you only need a sparse index in memory. You don't need to map every key, you just map the start of key blocks, allowing the system to quickly jump to the right block in the file and then scan forward from there. Much less memory needed for the index.
But if we're constantly appending new data, creating new sorted segments, how do we prevent the system from just running out of disk space with all these segments? And how do we ensure we're not reading old, overwritten versions of the data scattered across multiple segments?
That's where the real magic of compaction and merging comes in. This is the fundamental background engine of the LSM tree, that's log structured merge tree, which is used in popular databases like Cassandra, LevelDB, and Rocksteady.
Okay, how does compaction work?
When a segment on disk gets too large, or maybe it's just considered frozen after a while, a background process kicks in. It takes multiple existing segments, merges them together, remember they're already sorted, which makes merging efficient, throws away any duplicate or overwritten keys, keeping only the most recent version for each key, and then writes the combined compacted result out to a brand new segment file.
And the old ones?
Once the merge is successfully complete, the old fragmented segments that were used as input are simply deleted.
So the system is constantly doing this housekeeping work in the background, compaction and merging, to basically pay the price for having those really fast sequential writes happening in the foreground for new data.
Precisely. The LSM tree is essentially a cascade of these SS tables at different levels or sizes, constantly being merged in the background. The huge benefit is massive sequential I/O write throughput, making it ideal for systems with very high data ingest rates. The cost, however, is that reads can sometimes be slower or have more variable latency.
Why slower reads?
Because to find the absolute most recent version of a key, the system might have to check multiple SS table segments, starting from the newest and working backwards, plus potentially an in-memory structure, like a mem table, where the very latest writes reside before they are flushed to disk.
Okay, so LSM trees are great for write-heavy workloads. But despite their modern efficiency, the gold standard index structure for, well, the last 5 decades, really, remains the B tree. This is the core index found in almost every major relational database like PostgreSQL, MySQL, Oracle, SQL Server.
Yeah, B trees are also designed to maintain sorted key value pairs, enabling efficient lookups and range scans, but they achieve this via a completely different mechanism. Their structure is based on fixed-size pages or blocks, typically something like 4 KB or 8 KB in size.
How does the read operation in a B tree differ from an LSM tree scan?
A read in a B tree involves traversing the tree structure itself, starting from the root page, and following pointers down through internal pages, which contain key ranges, until you reach the correct leaf page. The leaf page contains either the actual row data, or, more commonly, a pointer to where the full row data resides on disk.
And writes.
Critically, unlike the append-only nature of LSM trees, when data is written or updated in a B tree, you typically try to overwrite the relevant page in place on the disk. If a page becomes full and needs to accommodate a new entry, it splits into two pages, and the parent page is updated with pointers to both new pages.
This sounds like random I/O versus sequential I/O again.
Exactly. This leads us right back to the central performance trade-off in storage engine design.
So B trees versus LSM trees. What's the bottom line?
Generally speaking, B trees are typically superior for random reads because the lookup path is very structured and guaranteed to be short. The height of a B tree is always logarithmically small relative to the number of keys. LSM trees, because they might need to check multiple merged segments in the mem table, can sometimes have higher or more variable read latency.
Writes.
LSM trees generally excel at write throughput because they rely almost exclusively on fast sequential I/O for appending data. B trees, relying on slower random I/O for overwriting pages in place, often have lower write throughput.
We also need to talk about the issue of write amplification, which is kind of a hidden cost associated with both approaches, isn't it?
Yes, it's a significant factor. Write amplification occurs when a single logical write operation requested by the application results in multiple physical write operations happening on the underlying storage device.
How does it manifest in each?
B trees suffer because even updating just a few bytes within a row often requires reading the entire 4KB page into memory, modifying it, and then writing the entire 4KB page back to disk. Plus, there's usually write into a write-ahead log, WAL, for durability first. So one small logical write becomes maybe 8 KB or more of physical writes.
And LSM trees.
LSM trees suffer write amplification due to that constant background compaction process we discussed. The same piece of data might be read, merged with other data, and rewritten to new segment files multiple times throughout its lifecycle in the database. This repeated rewriting amplifies the initial write. Managing this amplification is particularly crucial for maximizing the performance and extending the lifespan of modern solid-state drives, SSDs, which have finite write endurance. Hashtag 3.3. Transaction processing, OLTP versus analytics, OLAP.
Okay, now let's shift gears slightly and tackle the different types of loads or workloads that data systems are expected to handle, because it seems clear that one single storage engine or configuration can't possibly be optimal for everything.
We really need to distinguish between online transaction processing, OLTP, and online analytic processing, OLAP.
Yeah, these are fundamentally different beasts, designed for entirely different purposes. OLTP is typically the user-facing workload, processing customer orders, updating account balances, handling website interaction requests.
Lots of small, fast interactions.
Exactly. It's characterized by a very high volume of relatively small, low-latency requests. These requests usually involve only a small number of records, often accessed efficiently via an index, like fetching a user profile by ID. The primary performance bottleneck in many traditional OLTP systems is often disk seek time. How quickly can you locate that specific record on disk?
Whereas OLAP is about business intelligence, reporting, number crunching. Precisely. OLAP involves large, complex, often read-only queries run typically by business analysts or data scientists. Think about calculating the total sales revenue broken down by product category and region for the entire previous quarter.
Big aggregations.
Right. These queries scan over massive numbers of records, performing aggregations like SEMEM, average count, and groupings. The primary bottleneck here is usually not seek time, but maximizing sequential I/O bandwidth. How quickly can you stream huge volumes of data off the disk for processing?
Given these very different access patterns, the engineering response since, the late 1980s or early 90s has generally been to separate them entirely, moving those read-heavy analytics workloads onto a dedicated data warehouse.
Yes, that separation became standard practice. Data warehousing allowed architects to design and optimize the system specifically for OLAP query patterns, often favoring relational models, because SQL's powerful aggregation, grouping, and joining capabilities are ideally suited for complex analysis. The schemas used in data warehouses are also quite specialized, typically involving fact tables and dimension tables.
Okay, tell us about those. Fact tables record the individual events, right? The metrics, the raw transactions, and they can grow absolutely enormous.
They can. Fact tables often grow to hundreds of columns wide and potentially petabytes in size over time. They capture the core business events.
And they link to dimension tables?
Right. They link via foreign keys to much smaller dimension tables, which provide the context for the facts. The who, what, where, when, why. Think dimensions like customers, products, store locations, dates. These structures are commonly organized into what are called star schemas. a central fact table linked to multiple dimension tables, or sometimes more complex snowflake schemas, where dimensions are further normalized into subdimensions.
And the goal is flexibility for future analysis.
Exactly. The goal of this kind of denormalized design in a data warehouse is often maximum flexibility. You want to capture every potentially relevant raw event and attribute so that analysts can ask new kinds of questions later without having to completely redesign the data collection and storage system. Hashtag 3.4, column-oriented storage.
Okay, so if an analyst is querying a massive fact table in a data warehouse, maybe it has 100 columns and trillions of rows, they are likely only interested in maybe 4 or 5 of those columns for any specific query, like date, produced, quantity, price.
It's very typical, yes.
If the database uses traditional row-oriented storage, like most OLTP databases do, storing all columns for a given row together, it seems like it's wasting a huge amount of I/O bandwidth reading the other 95 irrelevant columns off the disk for every single row it processes. That sounds incredibly inefficient for OLA.
It is extremely inefficient for that workload, and this specific inefficiency was the primary driver behind the development of column-oriented storage or columnar databases. The core idea is elegantly simple, really.
What is it?
Instead of storing all the values belonging to a single row together contiguously on disk, you store all the values belonging to a single column together.
Yeah.
So you'd have one file or set of files containing just all the date values, another file containing just all the productive values, another for quantity, and so on for all columns.
Ah, okay. So if my analytic query only needs sales date and profit margin, the system only needs to load the file or files for the sales date column and the filelet S for the profit margin column. It can completely ignore the data for the other 98 columns on disk.
Correct. The system internally maintains the row order implicitly. For example, the 500th entry in the sales date column file corresponds to the 500th entry in the profit margin column file, allowing it to reconstruct rows if needed. This architecture immediately saves enormous amounts of I/O bandwidth by only reading the data that's actually required for the query.
And there's a massive secondary benefit that arises from this columnar layout too, right? Compression.
Yes, absolutely. Yeah. Column-oriented storage is typically highly compressible because all the values stored together in a single column file are of the same data type and often contain many repetitive values. Think of a regioned column where the same ID repeats for millions of rows. Compression techniques like run-length encoding or bitmap indexing become exceptionally effective.
And compression helps even more with I/O.
Definitely. Compression reduces both the storage footprint on disk and, crucially, the amount of data that needs to be transferred from disk into memory for processing, further enhancing that I/O bandwidth efficiency that's so critical for OLAP.
But once again, we inevitably face a trade-off. What's the price we pay for the superb read efficiency in columnar stores?
The price is usually write complexity and often slower writes, because a single logical row is now physically fragmented across potentially hundreds of separate column files. Performing updates or insertions becomes much more complicated. You have to potentially rewrite or modify multiple column files consistently.
So updates are hard.
Update and place operations, which are relatively straightforward in traditional row-oriented B-tree systems, become practically impossible or extremely inefficient in a pure columnar store. This is why column-oriented storage is almost universally confined to read-heavy OLAP data warehouses or analytics platforms, where the massive benefits of fast scanning and aggregation far outweigh the pain of potentially slower or more complex data loading and updates. Hashtag 4, encoding and evolution deep dive. Hashtag 4.1, the need for data encoding.
Okay, we've reached the final layer of our foundational discussion. How data is actually represented as it moves between different processes, maybe from application memory to disk or across the network between services. This is the fundamental challenge of data encoding.
Yeah, whenever data leaves the memory space of a single process, it needs to be encoded into a sequence of bytes. There are several categories of encoding formats out there, and each comes with its own set of risks, particularly around compatibility over time.
What are the main types?
Well, you still sometimes see engineers using language-specific formats like Java's built-in object serialization, or Python's pickle format. They often use these because they seem fast and easy to use within that single language ecosystem.
But they're dangerous, right? They seem to tie you hand and foot to that specific language and version, and they're notoriously brittle. If you change the class definition in your code base even slightly, the deserialization often breaks completely. They generally lack good backward or forward compatibility guarantees.
Precisely. They create tight coupling and are usually a bad idea for data that needs to persist or cross service boundaries. Then we have the ubiquitous textual formats, primarily JSON and XML. They are human-readable, which is a big plus, and fantastic for interoperability across different languages and systems.
But they have performance drawbacks.
They do. First, they tend to be quite verbose. They repeat the field names, like userid, for every single object or record, which adds significant overhead, especially for large datasets. Second, they can suffer from ambiguity, particularly when dealing with numbers. Is this string 123 an integer, a float, which precision, or representing binary data?
Which naturally leads us to the modern solution, often preferred for high-performance, resilient data pipelines, the binary schema-driven formats, things like Apache Thrift, Google's protocol buffers, often called protobufs, and Apache Avro.
Right. These formats require you to define a schema first, using an interface definition language, IDL. This schema explicitly defines the structure and data types of your records. The system can then use this schema to generate highly compact binary code. The schema provides all the necessary type information, which removes the need to include field names in the encoded data itself, resulting in dramatically smaller and faster encodings compared to JSON or XML. Hashtag 4.2. Schema evolution and compatibility.
Okay, so we have these efficient binary formats, but the ultimate test for any encoding format, especially in long-lived systems, is schema evolution. How well can it handle changes to the data structure over time? We need the ability to maintain compatibility when older and newer versions of our code, running simultaneously perhaps, must handle different versions of the data format. This seems unavoidable in any real-world distributed system.
It is absolutely unavoidable, and we typically need both directions of compatibility. Backward compatibility, which means newer code must be able to read data written by older code using an older schema, and forward compatibility, which means older code must be able to read, or at least gracefully ignore, data written by newer code using a newer schema.
That forward compatibility feels particularly crucial for systems that use things like message queues or databases where consumers of the data might lag behind the producers in terms of code updates.
Exactly. So how do formats like protobufs and Thrift achieve this compatibility?
How do they do it?
They rely on using numeric field tags instead of textual field names within the encoded binary data. In the schema definition, the .proto or .thrift file, each field is assigned a unique tag number. When the data is encoded, the field name is essentially replaced by its compact tag number.
Okay, so how does that help with evolution?
Well, if new fields are added to the schema in a later version, the new code just assigns them new, previously unused tag numbers. Older code, when encountering an unknown tag number during deserialization, simply ignores that field and skips over it. This maintains forward compatibility.
And removing fields.
If a field is removed, newer code just won't encode it anymore. Older code expecting that field might use a default value if one was defined in its version of the schema, or it might handle the missing field in some other way. Backward compatibility is generally maintained as long as you don't reuse tag numbers. The resilience is kind of hard-coded into the format via those mandatory tags.
Now, Avro, another popular binary format, handles compatibility in a fundamentally different way, correct? It apparently doesn't rely on those numeric tags being present in the encoded data itself, which can make the encoded data even more compact.
That's its key distinguishing feature. Avro often achieves the densest binary encoding because it omits the tag numbers and field names. But the trade-off is that in order to decode Avro binary data, the reading system must have access to both the writer's schema, the exact schema version used to encode the data, and the reader's schema, the schema version the reading code currently expects.
So the Avro library performs some kind of runtime resolution. It compares the two schemas side by side and effectively translates the data based on the differences it finds.
Exactly. This dynamic resolution based on comparing the writer and reader schemas is incredibly powerful. If a field name changed between versions, but represents the same logical data, the library can often match them up based on rules or aliases. If the fields in the writer's data are in a different order than the reader's code expects, the library can reorder them during decoding. Compatibility is generally maintained, provided that when fields are added or removed between schema versions, they have a default value defined in the schema. This dynamic, schema-driven translation makes Avro particularly well-suited for environments where schemas might be generated dynamically, for example, in ETL tools that automatically create Avro schemas when exporting data from large relational database dumps. Hashtag 4.3. Modes of data flow.
Okay, so encoding is necessary because data flows between different processes in various ways. Our sources identify three main modes of this data flow where encoding and evolution become critical concerns.
Right. The first, and perhaps most obvious, is data flow through databases. You write data to the database today, and it might be read back much later, potentially years from now, by a newer version of your application. Schema evolution here is largely about managing compatibility across time, ensuring today's code can still make sense of data written 5 years ago using an older schema.
The second major mode is data flow through services, which primarily happens using REST for public or cross-team APIs, and often remote procedure call, RPC, for internal, maybe performance-sensitive communication between microservices.
Yep. REST is generally simple and well understood, relying on standard HTTP methods and often using JSON for the payload. RPC, on the other hand, attempts to provide an illusion of transparency. It tries to make calling a function on a remote service look exactly like calling a local function within your own code.
And that illusion is precisely where the danger lies, isn't it? There's this famous critique called the illusion of transparent RPC.
It is deeply problematic, yes. RPC frameworks often try too hard to hide the fact that a network is involved between the caller and the callie. But networks are fundamentally unreliable. Calls can time out, packets can be lost or arrive out of order, remote services can crash halfway through executing a request.
Things you don't worry about with local calls.
Exactly. When a developer is led to assume that a remote call is just as reliable and instantaneous as a local function call, they often fail to build appropriate error handling and retry logic into their design, leading to potentially catastrophic systematic faults when network issues inevitably occur. This is why REST, by explicitly embracing HTTP's concepts of failure codes and latency, is often considered safer and more robust for external or less tightly controlled APIs, while high-performance binary RPC frameworks are usually best confined to well-managed internal data center environments where the network behavior is more predictable.
Okay, and finally, the third mode is message passing data flow, which typically uses an intermediary message broker or queue, like Kafka or RabbitMQ.
This mode is critical for achieving loose coupling between services. It's inherently asynchronous. The sender of the message simply publishes it to the queue or topic and doesn't need the recipient to be immediately available or even running at that moment. This addresses a core weakness of synchronous RPC.
The broker holds the message.
Right. Messages are stored temporarily or sometimes for longer periods in the broker. This positions message passing somewhere between the long-term storage guarantees of a database and the immediate request response nature of RPC. It's absolutely essential for building modern architectures that rely on event streams, asynchronous task processing, and decoupled microservices.
And some systems, like the distributed actor frameworks, akka is a good example, take this message passing model and apply it internally within a single application, scaling it across many nodes by treating all communication between actors as message passing. This seems to inherently model the failure risks of a network better than traditional RPC.
It does, because the actor model already assumes that messages might be delayed, lost, or arrive out of order, just like network packets. It forces developers to think about asynchronicity and potential failures from the ground up, which often leads to more resilient distributed application designs compared to trying to hide the network behind a leaky RPC abstraction.
Hashtag tag outro.
Wow, okay. This deep dive has really established, I think, the absolute foundations you need to consider when designing almost any high-quality, data-intensive application today. We covered the high-level goals, that constant struggle for reliability, scalability, and maintainability.
Then we analyzed the interface layer, comparing relational, document, and graph data models. We saw how that choice involves understanding historical context and making conscious trade-offs regarding join flexibility versus, say, application development simplicity.
We dug deep into the storage layer, contrasting the fundamental disk access patterns and trade-offs between LSM trees and B trees. We also clarified the dramatically different optimization targets required for OLTP versus OLEP workloads, including the clever efficiencies gained from columnar storage.
And finally, we examined that crucial communication layer. We tackled the need for efficient data encoding, the thorny complexities of achieving schema evolution compatibility across both time and distributed space, and the fundamental differences in coupling and reliability between synchronous approaches like RPC and asynchronous ones like message passing data flow.
Yeah, the overwhelming takeaway for me listening to all this is that successful data architecture seems to be the art of the compromise. Every single design decision you make, like prioritizing write throughput over read latency with an LSM tree, or prioritizing data model flexibility with a schema on-read document database, it always comes with a cost, a downside that has to be understood and actively managed by the engineering team.
That's perfectly put. And here's the provocative thought we want to leave you with, which leads directly into our next deep dive.
Yeah.
Almost everything we've discussed today, things like B-trees, sophisticated indexing, strong OLTP guarantees, they mostly work quite well, or are at least manageable on a single powerful machine. The real nightmare, the truly hard problems in data systems, begin when you are forced to break your stateful data across multiple machines, usually for reasons of massive scale or high availability.
That's where things like network failure, individual machine failure, and the incredibly complex challenge of achieving agreement among distributed nodes, what's known as distributed consensus, turns reliable system design from an engineering challenge into a struggle against the laws of physics itself.
That's where we had to tackle replication strategies, data partitioning schemes, and the often misunderstood implications of things like the CAP theorem and consistency models.
So stay tuned, because next time we find out what really happens when the network inevitably lies to you and how systems attempt to cope.
It's where the real fun and the real trouble begins.